Welcome to the second lesson of fourth module, which is on torsion part 2. In fact, in the last lesson, which was on the first part of the torsion, we have seen some aspects of the torsional moment which are applied on a bar, and we had considered that particular section, the cross section of which is a circular one and is a solid circular cross section, and we have seen the effect of the torsional moment in such cross sectional bar. Now, today we are going to look into, in this particular lesson, the effect of the twisting moment on such bar where the cross section is not a solid one, but a hollow one. So, what will be the consequence of the twisting moment on a bar, the cross section of which is a tubular one instead of a solid shaft? Let us look into that. Well, it is expected that once someone goes through this particular lesson, you should be able to understand the concept of twisting moment and its effect on bars of hollow circular cross section, understand the effect of non-uniform twisting moment and its effect on bars of circular cross section. And as we have done last time, that in the bar the twisting moment which was applied was uniform in nature. The bar was fixed at one end and the twisting moment was applied on the other end, and the bar was uniform. Also, the torsion applied over the bar was uniform in nature. Now, if there are some bars which may not be uniform, there could be variation in the section, or there could be uniform section, but the torsions applied at different point of different magnitudes. Now, if that kind of situation arise, then what will be the consequence of that kind of loading in the system, that we will look into, and that is what is the non-uniform twisting moment and its effect on bars of circular cross section, and thereby one should be able to evaluate stresses and deformation in circular bars due to torsion. Hence, the scope of this particular lesson includes, well, we will be looking into the aspects of the previous lesson as we have discussed, and that will be done through the answering the questions which I have posed, and also will be deriving the formulae for evaluating stress and deformation in bars of hollow circular cross section. Then we will be looking into the effect of non-uniform torsion on bars of circular cross section, and then we will be looking into the examples for evaluation of stresses and deformation in bars of circular cross sections of varying type. Now, we will be looking into the examples of bars with solid cross section, circular cross sections, or the cross section could be a hollow one like a tubular member. What is the effect of the torsion on such problems? And also, if we have different diameter of the bar, if we have a bar which is consisting of several diameters, and if it is subjected to torsion either of same magnitude or different magnitudes, then what is the consequence into such system? That we will be looking into through examples. Well, let us look into the questions that we had posed last time, and the first question which was given was, what is the type of stress a bar encounters when it is subjected to a twisting moment torsion? Well, let us look into the aspect which we discussed last time. Now, in this, if you remember that this is the bar which is having the cross section of a circular nature, and it is a solid circular bar which is subjected to a twisting moment T, and these we had defined as a positive twisting moment, because which is acting in an anticlockwise form and the thumb is projecting towards the positive x axis, which we have denoted as the positive twisting moment. Now, when this twisting moment is acted on this particular bar, and we had looked into a portion of the bar which is of length dx, and this is the part of that whole bar of length dx. Now, here we had evaluated, or we had seen, because of the effect of this twisting moment which is acting in this bar, if we take an element on the surface of this particular bar, this undergoes movement and thereby an helix is formed, and if we look into this particular element, this element undergoes a change in the angle, and this is the change in the angle, and as we had seen earlier that this change in the angle we call as shearing strain gamma, and thereby as per Hooke's law we get the stresses which gets induced into the surface, which we call as the shearing stress. So, basically what we get is, because of the application of the twisting moment in the bar, we get shearing stress in the bar, and because of this shearing stress, now this here is without any application of the normal stress. So, we call this is the state of pure shear, and this state of pure shear can be transformed in terms of Mohr circle to evaluate the normal stress, the maximum normal stress. Now, if you remember that if we plot this state of stress in the Mohr circle, this is the sigma axis and this is the tau axis. Now, here we have negative of, because this is clockwise movement by this particular shear on this face. So, this is as per our notation, this is a negative shear which is plotted on the top side of the Mohr diagram, and for the other side we have a positive value which is plotted over here. So, this is the value of tau, and this if we plot as a circle, this is the center, and if we plot the circle, then we get the value of the normal stress that will be acting, and this is the value of the normal stress. Maximum normal stress is this, which is sigma 1, and the minimum normal stress is this, which is sigma 2. Now, interestingly, if you look into the values of sigma 1 and sigma 2, both are equals to tau. So, basically due to the application of the twisting moment, the bar is subjected to a shearing stress, and thereby we are going to get the normal stress, which are also the magnitude wise equivalent to the shearing stress. Only the angle here is 90 degree. So, the action of this principal stress will be at an angle of 45 degree with respect to this shear, and that will be the maximum normal stress, which is equals to the value of tau. Now, let us look into the application of such a twisting situation that we come across if when we move a screwdriver. This is the application of a twisting moment, and this gives you, if you can look into the figure, you will see that when we are rotating it, basically we are applying the twisting moment, which is allowing this to rotate and finally moves inside. Well, let us go back to the question which we had asked the next, which is what is meant by torsional stiffness. The second question asked was that what is meant by the torsional stiffness. Now, let us look into the expression which we had derived last time for the torsional moment. Now, this is the expression which we had derived, which we call as T by j equals to tau by rho is equals to g theta by L, and if you remember, T is the twisting moment, j we had termed as polar moment of inertia. This is polar moment of inertia. Tau is the shearing stress, rho is the radius at any point from the center of the cross section, g is the shear modulus, theta is the rotation, and L is the length of the bar. So, this is the expression which we call as a torsion formula. Now, from this, if we equate these two quantity, now what we are interested in is to find out the stiffness because of the torsion. Now, when we apply the twisting moment, now the twisting moment required to produce unit rotation is generally called as the stiffness against this twisting moment. So, twisting moment required is to produce unit rotation is termed as the torsional stiffness. So, if we equate these two quantities, that T by j is equals to g theta by L, then we can relate T and theta as T as equals to g j by L times theta. Now, if we make theta as unit, then T is the torsional stiffness. So, torsional stiffness in other words is equals to g j by L. So, this quantity is designated as the torsional stiffness. Now, if we look into the units, now G is the one which is represented in terms of megapascal, J is the polar moment of inertia which is millimeter to the power 4, and L is the length which is in millimeter. So, we have Newton per millimeter square, and then we have J which is millimeter to the power 4. So, this is millimeter. So, you have Newton millimeter as the unit for T, which is equivalent to the unit for the twisting moment. So, this is the stiffness that we have. Now, the third question was that what will be the stresses and deformation due to torsion if the bar is hollow circular section instead of a solid one. Now, this is the aspect in fact which we are going to discuss today. So, this question will be answered through the discussions which we will be going through in this particular lesson. So, let us look into that aspect, that how do we calculate the effect of the now torsion in the circular tubes. Now, in the previous lesson we have gone through that if a bar which is of solid circular section is subjected to a twisting moment, then when it is subjected to a twisting moment, it is subjected to the shearing strain which we have seen, and gamma is equals to d theta by dx times rho. This is the expression which we had looked into for the solid shaft, and gamma is the shearing strain at any point which is at a radius rho, and d theta dx we have termed as the rotation per unit length. Now, this particular expression which we had derived for the solid circular section in fact is equally applicable for this hollow tubular section as well. That means, at any point from the center of the tube as we go along, as we had seen in case of solid circular shaft, that at any point from the center at any radius rho we can compute the strain gamma. Now, in this particular case from the center till we reach to the inner point of the tube there is no material. So, thereby there is no strain. So, the minimum strain that occurs is at the point which is the inside of the tube. So, if we look into this tubular cross section, now this is the center over here. Now, let us call that this radius, internal radius as r 1 and the external radius as r 2. Now, coming back to this expression again, the maximum strain that occurs gamma max is at the outer periphery, where if this is the outer periphery of the whole tube, and if we have call this radius as r, then when rho becomes r, that gives us the value of the strain as gamma maximum. So, gamma max is equals to d theta dx times r. So, this is what we get in case of solid circular shaft. Now, when we come to this tubular form, now the first material from the center it encounters is at the inner radius. So, the minimum strain that occurs is at this particular point, and the maximum strain occurs at the outer radii. So, these are the points, and as we had seen from this particular expression that gamma varies with rho linearly. So, the strain varies linearly with the radius, and so as the stress from our Hooke's law, that tau is equals to g times gamma, since gamma is d theta dx times rho. So, g d theta dx times rho, again g d theta dx being independent of rho, tau varies linearly with rho. So, the shearing stress varies linearly with the radius from the center. Now, here in case of hollow tube, the same theory holds good, only thing is that since we do not have any material at the center, now the first point which encounters stress is at this particular point, and then as it goes along the outer periphery, here we have the maximum stress. So, the variation of the shear stress across thickness is in this form, which is proportional to the radius rho. So, this is the distribution of the shear stress in case of tubular section. So, the same theory as we had in case of circular shaft holds good even for the tubular section as well. Now, let us look into that how we relate the different quantities as we had related in case of solid shaft, like the shear stress to the torsional moment, the radius at which point we like to find out the stress, and then corresponding quantity of the rotation, the shear modulus and the length of the bar. So, let us look into that how do we compute this relationship in case of tubular sections. Now, coming back to this expression which we had, gamma as equals to d theta dx times rho. Now, we know that the shear stress tau is g times gamma is equals to g d theta dx times rho. Now, as we had seen, this is basically from the compatibility criteria. Last time if you remember, when we were discussing the derivation of the formulae for the torsion, when the torsion is applied the corresponding stresses, we had equations of compatibility which is in terms of the rotation, and subsequently we had the equations of equilibrium. Now, equilibrium equations are derived mostly from the stress resultant that is being generated because of the twisting moment. So, on any cross section the stress resultant is equals to the applied twisting moment, and same concept we apply here to evaluate what should be the expression or the relationship between the stress and the twisting moment. Now, if we consider a small element, let's consider a small element in this now let us consider a small element from the center, say which is at a distance of rho and making a small angle, let us say as d alpha. So, this is the small element having an area dA at a distance of distance rho, and this distance is d rho. So, the area, and let us call that this small angle is d alpha. So, the area dA can be written as rho times d alpha times d rho as the area. Now, the force that will be carried by this particular area is equals to the shearing stress times area. So, dP is equals to tau times dA, and this is equals to, if we substitute for tau from this expression, this is equals to g times d theta dx times rho times dA. Now, if we take the moment and this dA now, if we substitute in terms of d alpha d rho, this is equals to g d theta dx rho, that is rho square d alpha d rho. Now, the twisting moment that will be acting in this particular section, this is T, and that will be resisted by the whole of cross section, the integral of dP. So, twisting moment T is equals to integral dP. Now, here we have two variable, one is alpha, another is rho. Alpha varies from 0 to 2 pi and rho varies from r inside r 1 to r 2. This is r 2 and this is r 1. So, this is 0 to 2 pi for alpha and from r 1 to r 2 for the rho. So, this is equals to integral g d theta dx times. Now, here we have rho and this is dP times rho is the twisting moment. Now, here we have a rho and this rho d alpha dA. So, this is rho square and this times rho is rho cube. So, this is rho cube times d alpha times d rho. Now, this g theta d theta dx being constant, this is from 0 to 2 pi and from r 1 to r 2. Now, if we take out d theta dx, now let us remove this part. And let us evaluate now that t is equals to g d theta dx. Now, d alpha, integral of d alpha is alpha, which is varying from 0 to 2 pi. So, that is equals to twice pi, and then we have rho cube d rho. So, this is rho 4 by 4, and if we integrate from r 1 to r 2, that is 1/4, then r 2 to the power 4 minus r 1 to the power 4. So, this we can write as g d theta dx pi by 2 times r 2 to the power 4 minus r 1 to the power 4. And if r we write in terms of diameter, then this is equals to g d theta dx. Now, r is twice the d outer, and d 2 is d outer, d 1 is d inner. So, this is 16. So, pi by 32 times d 2 to the power 4 minus d 1 to the power 4. So, this particular term, as you remember last time we had designated that as j, which is nothing but equals to the polar moment of inertia. So, this is j. Now, if you compare the value of j with respect to the j which we have computed for the solid shaft, j for solid shaft we had pi d 4 by 32 for the solid one. Now, here the value of j in case of hollow section, where d 2 is the outer diameter and d 1 if it is the inner diameter, then in terms of d 2 and d 1, j is equals to pi by 32 times d 2 to the power 4 minus d 1 to the power 4. So, virtually this is similar expression, and this you can visualize that from the whole one we are removing the central part. In fact, basically as you can see in case of solid circular shaft, that when if you take out the material, because the shearing strain or the stresses are varying from the center to the outer periphery, it is 0 at the center and it is maximum at the outer periphery. Now, if we remove the material from the central portion, the stress maximum stress wise we are on the outer periphery. At the same time, when we are equating the forces, when we are getting the equilibrium equations, now if we take the element away from the center, we get larger contribution. So, the material which is having closer to the center has less contribution in comparison to the material which is away from the center. Hence, in that sense tubular sections will be more effective when resisting the twisting moment, and that we will be looking into subsequently when we will be solving the examples. Well, so this is the value of the j, and from based on this particular expression. So, this is the twisting moment t, t is equals to g d theta dx times j, and over the length if we integrate, we get t as equals to g theta j over L, and this expression we had seen last time, that t by j is equals to g theta by L. Only difference is the expression for j is different now for the hollow tube than what we had in case of solid shaft. Now, this particular expression for the polar moment of inertia can be written down in a different form as well. Let us look into that j, value of j, the polar moment of inertia, we have got in case of tubular section as pi by 32 times d to the power 4 minus d 1 to the power 4. Now, we can simplify a little, and many a times we use this expression as, let us say, pi by 32 times, we can write this as d 2 square square and minus d 1 square square. So, this is square of d 2 square minus square of d 1 square, and this gives us pi by 32 times d 2 plus d 1 times I am sorry d 2 square plus d 1 square plus d 2 square minus d 1 square. Now, further d 2 square minus d 1 square can be split and we can write this as pi by 32 times d 2 minus d 1 times d 2 plus d 1 into d 2 square plus d 1 square. Now, d 2 minus d 1, as you can visualize that when we have the tubular form, the outer diameter is d 2, outer diameter is d 2 and the inner diameter is d 1. So, from d 2 if we subtract d 1, we are left with. So, this is d 1, this is d 2. From d 2 if we subtract d 1, we are left with two thicknesses. So, this we can write as twice t. If t is the thickness of the tube, we can write this as twice t. Now, this term d 1 plus d 2, we can designate this as average diameter and we can write this as d as equals to d 1 plus d 2 by 2. Now, d 1 plus d 2 by 2 is the average diameter d. So, d 2 plus d 1, if we write that as twice d into twice d times. Now, this particular term d 2 square plus d 1 square, we write in a little different form as d 2 plus d 1 square plus d 2 minus d 1 square divided by 2. Now, again as you can see from by writing this d 2 square plus d 1 square term in this form, d 2 plus d 1 we can write as twice d and d 2 minus d 1 we can write as twice t. So, this is equals to, now 2 to 4 gets cancelled with 8. So, this is pi divided by 8 times d times t multiplied by, now d 2 plus d 1, this term again we can write as twice t d and twice d square means 4 d square plus d 2 minus d 1 is twice t. So, this is 4 t square divided by 2. So, this comes out as pi by 8 pi d t multiplied by 4 d square plus t square divided by 2. So, this gives us a value of pi d t divided by 4 times d square plus t square. In fact, this is a simplified form of this particular expression j. Many times if we can represent the diameter in terms of average diameter, we can use this expression for evaluating the polar moment of inertia instead of pi by 32 d 2 to the power 4 minus d 1 to the power 4. Also, many times we use a shaft or a bar, hollow bar, the thickness of which could be significantly small in comparison to the radius of that particular tube. In that particular case, the term d square, the term t square will be very small in comparison to d square. So, if we neglect that and if we write approximately this d square plus t square term as equals to d square, then we get this as pi d cube t by 4. Now, sometimes for a thin tube we approximate the polar moment of inertia using this expression pi d cube by t times divided by 4. So, this gives us the value of the j, the polar moment of inertia, either in this form which is pi by 32 d 2 to the power 4 minus d 1 to the power 4 or pi d t by 4, where d is the average diameter, t is the thickness times d square plus t square, or for a thin tube we can even use this pi d cube t by 4 for evaluating the polar moment of inertia. Now, once you do that, once you compute the polar moment of inertia, then rest of the expressions as we had, that tau by rho is equals to t by j is equals to g theta by L. Now, we can use this equation again for evaluating the stresses, and the terms as we have defined earlier remains as it is, like tau is the shearing stress, rho is the radial distance, and here the rho becomes effective between R 1 to R 2. Below R 1, since there are no materials, hence it is not effective, and T is the twisting moment, J is the polar moment of inertia, G is the shear modulus, theta is the angle of twist over the whole length of the bar, and L is the length of the bar. So, the same expression as we had used for the solid circular shaft is equally applicable for the tubular section as well. Only difference is that the polar moment of inertia has to be computed in a different form than the solid circular shaft. Well, having looked into the effect of the torsion on a tubular section, let us look into that if we have a section which is not uniform. Now, so long we were discussing about the effect of the torsion on a bar which is uniform. Now, whether the shaft is solid or it is hollow, the bar was uniform. Now, if we have a non-uniform bar where over the length of the bar the diameter varies, and if it is subjected to a twisting moment at one point, or if we have the twisting moment acting at different point of different magnitudes, then what is the consequence of that twisting moment over the bar, or how do we compute the stresses and the deformation in such bar where the bar is not uniform or where there is variation in the twisting moment. Let us look into that. Now, if we have, let us take a bar where the length is varying and also we have the change in the diameter. Let us call this diameter as d 1, maybe here this as d 2, where this is varying, and let us say this is d 2. And let us assume that this is acted on by the various twisting moment at different point. Let us call this bar as say A, B, C and D. Now, at these points A, B, C, D, different twisting moment T 1, T 2, T 3, T 4 they are acting. Now, when there will be twisting moment acting into it, now if we draw the free body diagram say between A and B, now the twisting moment T 2 is acting at the point B. Now, between A and B we have only the twisting moment T 1 acting. So, if I take a section here and draw the free body diagram between A and B, then we have the part A B, this is just before B, before the application of T 2. So, we have a twisting moment acting in this. So, this is on the, so far as the application wise is concerned, this is again has the positive kind of a twisting moment. Now, as we have defined, now here we have the twisting moment T 1 acting into it, which will be opposing this. So, this is T 1. So, over the length A B, if we say length A B as L 1, we can compute the value of the stress from our relationship that tau by rho is equals to T by J over the length L, and this gives us a stress tau which is equals to T times rho by J, and this T here is equals to T 1 for the present case, and over the length A B this will be the stress. Now, if we consider a segment between B and C and if we cut off, then the twisting moment that will be acting here it is T 1, here we have T 2. Now, as per our notation this is positive, this is negative. Now, so we will have twisting moment, let us write again in a positive sense which is acting in this, and if we call this as T. So, T is equals to T 1 minus T 2. So, for this resulting twisting moment T between that will be acting between B and C. So, we compute the stress again over the length B C. Now, this is the twisting moment T which is equals to T 1 minus T 2, this times rho by J. Now, assuming here this is a uniform diameter, we will be discussing this aspect at a later time, that when it is varying. So, if you have a uniform diameter over that particular stretch between B and C, then the stress again is the resulting twisting moment which is T 1 minus T 2 times rho by J. Now, if we take a section between C and D, if we cut off over here, then we have T 1, we have T 2, we have T 3, and T1 and T3 they are acting in the same direction and T2 is in the opposite direction. So, the resulting T for that will be equals to T1 plus T3 minus T2. So, and since this is in the anticlockwise direction which is positive and we are considering T also as anticlockwise and positive. So, this will be the whole thing will be negative. So, if this expression becomes negative, then it will be in the opposite direction as we have assumed, and if the whole expression becomes positive, then the assumed direction will be same as we have assumed over here. So, that is how we compute the resulting twisting moment, and once we have this resulting twisting moment, we compute the stress using this expression. Now, when we come to the evaluation of the rotation, now as you can see that we have 3 different segments over which we got to compute we have computed the equivalent T. Now, here we have T 1, now here we have T bar as equals to T 1 minus T 2, and at this point we have T 1 plus T 3 minus T 2. So, these are the resulting twisting moment that we had. Now, this twisting moment which is acting over different lengths will have different rotation. Now, for the first segment where T 1 is acting over length A B, so it will undergo a twist. At length after B, between B and C, there is a resulting effect of the twisting moment T 1 and T 2. Now, T 1 is acting in an anticlockwise direction and is trying to rotate the shaft in one direction, whereas T 2 is acting in the other direction, where is trying to nullify this rotation to certain extent. So, there will be change in the rotation. So, what we do over the different segments A, B, C and D, over length A B which is L 1, let us call this as L 2, let us call this as L 3. Now, over length L 1 we compute what is theta. Now, as you know that T by J is equals to G theta by L, or from this we can write theta as equals to T times L by G J. Now, for the first segment A B, theta A B will be equals to T 1 L 1 by G J, and J also will be corresponding to the diameter, let us call this as D 1. So, we will get the value of theta A B. Then we compute again theta B C, considering the resulting twisting moment times the length which is L 2 G and J considering the diameter D 2 over B C. We evaluate theta C D from the resulting twisting moment which is T double bar equals to T 1 plus T 3 minus T 2 times L 2 and G J over D 3. Now, once we compute these 3 thetas, theta A B, theta B C and theta C D, then the final theta will be the sum of these with its appropriate sign, that theta A B plus theta B C plus theta C D. Now, when I am calling this as with appropriate sign, it means that if the twisting moment is in a positive direction, it is causing a positive rotation. If the twisting moment is in the negative direction, it is causing the rotation in the negative rotation. So, if at different segments we consider these 3 different rotations with appropriate sign and sum them together, we will know that the shaft which is of varying diameter and varying length between these 2 points will be undergoing how much net rotation, and that is what is our contention to evaluate. So, now if we look into the evaluation of the stress and the deformation because of this non-uniform distribution either in the material diameter wise or in the change in the twisting values. So far as the stresses are concerned, when you compute the stresses for different segments, the maximum stress out of all these segments, whichever will give the maximum value, that will be the governing stress, and the rotation wise between the 2 ends we will sum them up and the final rotation will be the rotation in the shaft which will be governing. So, these are the 2 aspects which are little different than if the bar is uniform and subjected to uniform twisting moment. Well, with this background, let us look into some of the examples wherein we apply these theories. Now, this particular example in fact, I had said for you last time, and I had asked you to evaluate. I am sure you got the values for this. Let me just give you the values so that you can compare your results. A solid aluminum bar of length 1.2 meter and 25 millimeter diameter is twisted by torque T acting at the end. That means, if you have a solid aluminum bar which is subjected to a twisting moment, and this is our positive twisting moment notation. That means, we are giving the vectorial notation over here, and the length of this bar is 1.2 meter, diameter is 25 millimeter, and this is twisted by torque T. Now, the shear modulus is given. What you will have to find out is the torsional stiffness of the bar. Now, in the light of the discussions we had today, that what will be the torsional stiffness when it is subjected to a twisting moment T, as we have defined that torsional stiffness is the one where the twisting moment required to produce unit rotation, we call that as a torsional stiffness, and the value of which we have seen as G j by L, and we got to compute that quantity, so that we know how much is the torsional stiffness. So, let us compute this value of the torsional stiffness. Now, we know that T by J is equals to G theta by L, and T thereby is equals to G j by L times theta. Now, as per our definition, theta is unit. So, this is the stiffness. So, G j by L. So, this is equals to, now the value of G here given as 0.3 into 10 to the power 5. Now, the value of J, the polar moment of inertia, the diameter given as 25 millimeter. So, J is equals to pi d 4 by 32. So, this is equals to pi times 25 to the power 4 divided by 32, so much of millimeter to the power 4. So, this is the value of J. So, G j by L, this quantity is equals to 0.3 into 10 to the power 5 into J is 5 into 25 to the power 4 divided by 32, and L is equals to 1.2 meter. So, this is 1200, so much of millimeter, and this gives us a value of 958.74. This is so much of Newton meter. Now, as I told you that the unit wise G is MPa, which is Newton per millimeter square, J is millimeter to the power 4 divided by L is in meter, a millimeter. So, this cancels millimeter square and this cancels millimeter. So, Newton millimeter. So, this is what is in Newton meter. So, this is the torsional stiffness of the bar which is subjected to a twisting moment. Now, the next step is to calculate the, if the angle of twist of the bar is 5 degree, if the angle of twist of the bar is limited to 5 degree, then what is the maximum shear stress? Now, in the same bar, when it is rotated and if the angle of twist between the length is restricted to 5 degree, then what will be the stress, maximum shear stress that will be generated on the surface of the bar. Now, let us look into this particular part of the example. So, again we know that T by J is equals to tau by rho is equals to G theta by L. So, the stress tau is equals to T times rho by J. Now, and also this is equals to G rho theta by L. If we equate these two, we get the shearing stress tau as equals to G rho theta by L, and this is equals to 0.3 into 10 to the power 5, rho is 25 by 2 and theta is 5 degree. So, in terms of radian if we write, this is 5 pi by 180 divided by L is 1200. So, this is equals to 0.3 into 10 to the power 5 into 25 into 5 into pi divided by 2 into 1200 to 180. So, this is so much of MPa or Newton per millimeter square is the shearing stress tau, and this value comes as 27.27 MPa. So, here the value of shear modulus is given, the radius rho is given which is d by 2, theta is limited to 5 degree and length of the member is known. So, we have computed the stress in terms of this from this limiting value. So, the maximum stress that will be generated on the surface is equals to 27.27 MPa. Okay. Now, let us look into the another example. Now, in this example we have a hollow aluminum tube. This is interesting. In fact, this is discussed in light of the problem which we have discussed today. It is a tubular section. So, we can make a comparison between a solid section and a tubular section. Now, a hollow aluminum tube used in a roof structure has an outside diameter of 100 millimeter and inside diameter of 80 millimeter. The tube is 2.5 meter long. The shear modulus is given. Now, if the tube is twisted in pure torsion by torques acting at the ends, then what is the angle of twist when the maximum shear stress is 50 MPa. So, we will have to find out what is the angle of twist when the maximum shear stress is limited to 50 MPa. And secondly, what diameter is required for a solid shaft to resist the same torque with the same maximum stress. So, we can make a comparison between the two, and what is the ratio of the weight of the hollow tube to the solid tube. So, let us look into this particular example, so that we can make a comparison between the two. Now, the diameter outside d outer is equals to 100 millimeter, d inner is equals to 80 millimeter, L the length of the member is 2.5 meter, G given as 28 GPa. Now, tau is to be limited to 50 megapascal, and corresponding to that we will have to find out what is the rotation. So, now that we know tau by rho is equals to g theta by L. Now, we are taking this relationship because shear stress is limited, we will have to find out theta. So, this gives us theta as equals to tau times L by g times rho, and if we substitute this value, tau is limited to 50 MPa, length of the member is 2500 millimeter, G is 28 GPa times 10 to the power 3 so much of megapascal, and rho. Now, rho is the maximum shear stress will occur on the outside face. So, the outside diameter is 100. So, the rho here is 50. So, this gives us a value of theta which is equals to we get the value of theta as 0.0898 radian, and this when we compute in terms of the degree. So, this is equals to 0.0898 into 180 by pi, this will give us degree. So, this is 5.12 degree. So, this is the maximum rotation that we can expect when we apply the twisting moment and if we limit our stress to 50 MPa. Now, let us look into that if we go for a solid section instead of the hollow one, then what will be the diameter of that. Now, for that part again we need to compute the value of twisting moment. Now, T by J is equals to tau by rho we know. So, tau times J by rho will give us the value of the twisting moment, and J for this particular section is pi by 32 times d 2 to the power 4 minus d 1 to the power 4. which is equals to 5.8 into 10 to the power 6 millimeter to the power 4 in this particular case. And from this, if you compute the value of t, tau we know which is 50 MPa, we will have to limit to, j is this, and rho is the maximum outer diameter corresponding to the maximum stress, and that if we substitute, this comes as tau as 50 times 5.8 into 10 to the power 6 divided by 50. So, this is equals to 5.8 into 10 to the power 6 so much of Newton millimeter. So, this is the twisting moment. Now, corresponding to the twisting moment, we will have to find out the diameter. Again, from T by j is equals to tau by rho, and from this if you write that T is equals to tau times j by rho. So, this gives us the j is pi d 4 by 32 and rho is d by 2. So, this gives us pi d cube by 16. So, this is equals to tau pi d cube divided by 16. So, this is the value of t in terms of the stress. Now, what we need to compute is the diameter d. So, from this particular expression, if we compute the value of d, now d cube is equals to 16 t divided by tau times pi. So, this is equals to 16 into t we have got as 5.8 into 10 to the power 6, tau is limited to 50 times pi, and from this if we compute, d comes as 84 millimeter. Now, you see this is the diameter which we are getting for a solid shaft or solid bar against a tubular one, which is having outer diameter as 100 and inner diameter as 80. Sorry, this is the diameter. So, outer diameter as 100 and inner diameter as 80, and as opposed to that we have a solid section which is of 84 millimeter diameter. Now, if we like to compute, if we like to compare the weight of these two elements, basically the ratio between the weight of hollow and the solid will be in the ratio of their area, because if we take per unit length and if we take the same material, so naturally the unit weight is the same. So, the ratio of the area will give their weight ratio. So, ratio of their weight, this is equals to, let us call this is the area of tube by area of solid, and this is equals to the tubular area is pi by 4 times 100 square minus 80 square, this divided by pi by 4 times 84 square. So, this is for the solid area, and if you compute these two, you will get a value of 0.51. So, you see that for resisting the same amount of stress under the same twisting moment, we have the area of the hollow cross section, which is 50% of the solid area. So, we are making some savings in terms of the material. So, that is more effective when you are resisting the twisting moment or applying the twisting moment. Well, we have another example for you. Now, a step shaft ABCD consisting of a solid circular segments is subjected to 3 torques. Now, this is A, this is B, this is C and this is D, is subjected to 3 torques as shown over here, and the values of G is given. You will have to calculate the maximum shear stress in the shaft and calculate the angle of twist at D. Now, look into this example, I will be discussing next time. Now, we have another example also for you, which is a solid circular bar ABC consists of 2 segments as shown over here in the figure, and what is the allowable torque in the entire shaft if the shear stress is not to exceed 32 MPa and the angle of twist between the ends of the bar is not to exceed 1 degree. Now, here 2 criteria are set, that the stress cannot exceed beyond 32 MPa and the total angle of twist cannot go beyond 1 degree. Now, here you have different diameter of the shaft, the total shaft is consisting of 2 different diameters, but it is subjected to one twisting moment. So, you will have to find out that what should be the shear stress, I mean what is the allowable torque that you can apply on this particular shaft if the stress and the rotation is limited. Well, then to summarize what we have discussed in this particular lesson, we have discussed the concept of torsion in a bar of hollow circular cross section. Now, in the previous lesson we had discussed about the solid section, a bar which is having a solid cross section. In this particular lesson we have discussed the effect of torsion on a bar where the cross section is a tubular one and is not a solid one. Then concept of stresses and deformation in a bar of circular cross section due to non-uniform torsion, and then we have looked into some examples to evaluate stresses, strains and deformation in bars of circular cross section due to torsion. Now, the questions which are set for you are: which section is effective in carrying torsion, whether a solid one or hollow circular one? What is the effect of torsion on bars of varying diameter, and what is the value of minimum shearing strain for bars with solid and hollow circular sections? Well, these questions we will be discussing in the next class. Thank you very much for your attention.